there is no best viewpoint. And that best viewpoint is subject to the question. We should not say this is the way to look at it, everything else is bad, and so on and so forth. Contradictory sounding views are sometimes necessary to understand the subject. Openness and the fact that duality shows us that multitude of attitudes and views is important to appreciate and connect, not only in a scientific context, but in a broader human societal aspect, I think would have a good applications.
Welcome, everybody, to this edition of the Into the Impossible podcast. I am your fearful host, Brian Keating, and today it is a great pleasure, a treat, in fact, for me to welcome none other than Cumrun Vafa of Harvard University. How are you, Cumrun?
Thank you very much, Brian, for having me in your program. It's a great pleasure. I'm fine and looking forward to our discussions.
Yes, I've been just devouring your book, which we're going to talk a lot about today, Puzzles to Unravel the Universe. And I've been fascinated with puzzles my whole life, mostly my inability to solve them. But you are noted for having made tremendous contributions to the world of theoretical physics. And this is your first popular science book, as I understand it. And I always like to say there's a piece of advice that you never should judge a book by its cover. But on this book, not only do you have a very mysterious and puzzling imagery, but you also have endorsements in Comia from none other than Edward Witten, who I've tried to get on the show unsuccessfully, but I'll talk to you about that later. And also Brian Greene, another Brian, actually my kid's favorite Brian in astrophysics. But I want to ask you, how did you come up with the name of the book, Puzzles to Unravel the Universe? And how did you come up with the artwork that so beautifully graces the cover of this book?
The title, I think, was motivated by a course I'm teaching for Harvard freshmen called Physics, Math, and Puzzles. It's a freshman seminar. And so the book was basically, it was grown out of this course. And so I decided, I was thinking about what title to choose. If I had chosen Physics, Math, and Puzzles, it sounded a little bit maybe boring. So I thought maybe I should use some elements of it without sounding too academic and a bit more kind of exciting in terms of applications to the real world and so on. So I thought that, which involves actually the motivation behind the whole course, which is the connections with the real world. So I thought unraveling the universe through puzzles to unravel the universe does justice to what I wanted to convey. And that's why I chose that. As far as the book cover, I got some help from some people from online, but this whole design and all that happened during the pandemic. So I decided during the pandemic, one thing I could do is to finish this series of notes into a book, which I decided to do and self-publish it just to go over, to get it quickly out and get it done. So that it's people who may want to be looking at it could have a chance to do it during the pandemic as well. So it was done in a bit of a speedy way at the end, but so that's what it is. But I'm very happy with the cover of the book as well as the way the book came out.
Yes, it's very intriguing and it matches the subject matter as well. I want to make a distinction between mysteries and puzzles and wonder if you do that as well. To me, there's a difference between a mystery and a puzzle. And I once discussed this with Freeman Dyson, who I know you knew, the late, great Freeman Dyson. And it was that, a puzzle is something that could be solved. Maybe I can't solve it because I'm not as smart as you, but a mystery might not be solvable. And I wonder, do you make a distinction between mysteries versus puzzles?
Well, in a sense, puzzles aspire to be mysteries. That's the way good puzzles aspire to be like mysteries. That's not quite solvable, but gives you an inspiration to new ideas. So I view puzzles always like that. But I think, for example, in the book, I talk about the enigma of quantum mechanics. I still view it as a mysterious features that we encounter, even though we think we understand quantum mechanics. The features of experimentation within quantum mechanics are mysterious still to me. And so in that sense, I agree, we haven't solved it, or it's not solvable at this point. It might continue to be mysterious, or maybe it gets resolved in a different form. Similar things happen like black holes. We have similar enigmas about black hole and mysteries about black hole. Puzzles are pieces which kind of, as I say, try to get some features of these mysteries in some little nuggets of truth, and you can kind of wrap your mind around it and kind of understand it at least. So there's kind of there's a distinction, but there's this relation. They want to reinforce each other. That is, you're hoping that the mysteries become like puzzles that you can solve. That's the way I look at it.
Yeah, I looked at puzzles. I remember the most famous one, perhaps, is Rubik's Cube. Is a puzzle that I became infatuated with as a kid in the early 1980s. I think it's just about 40 years old, or maybe a little bit older, made by, I believe, a Hungarian named Rubik, and became fabulously wealthy. And his whole life is wrapped up in this particular cube, and it's even such to the point that he cannot really sleep when he tries to solve it faster than his previous record, et cetera. There are all these competitions, and he can't really do it as well as other people could. Or when he was a younger man, he could solve it even faster. I wonder, if you look at your career, is there a particular puzzle or mystery that you're most fascinated by among the many things you just mentioned, quantum mechanics, black holes? Later, we'll get into string theory. Are there things that just keep you up at night and that you won't rest until you solve them, or perhaps make some contribution towards the understanding of them?
Good problems have interesting reformulation in terms of things we can understand clearly in terms of the model that we are approaching. So there are many examples that comes to my mind. The computation of the entropy of the black hole, for example, using ideas about how you count the string theory degrees of freedom using the geometry of string compactification. The work I did with my collaborator Andy Strominger is an example. But there are many such things, and I don't think I will just pick one particular ones. I think even some of the papers that may not be as well received or as well known in general, I still might enjoy some of the puzzles that I can encounter. And to me, it's hard to calibrate it and organize it in terms of the ranking of which one is higher or lower in terms of interest to me. But even trivial sounding puzzles could be interesting, and I find interesting. So many of the puzzles that I discuss in the book, on the face of it might sound like, okay, so what? It's so simple. What do you want to learn? But even those simple ones, I kind of think even after I've solved it and discussed it for 10,000 times, I still enjoy thinking about it. So I think it's like the aftertaste of the puzzle is what attracts me to thinking, because it gives you a springboard for other ideas. It gives you, say, oh, maybe this thing means a bit more something else, and you begin to think. So it might sound by itself kind of like a boring statement, but the connections and what else it might relate to is what fascinates me.
Yeah, I think it was maybe it was Albert Michelson, I think he was the first U.S. Nobel Prize winner, or one of the first Nobel Prize winners from America. And he said, experiments are like puzzles to a kid. And just like a kid will do a puzzle, even once he or she has solved it, he'll do it again or she'll do it again, because every time they do it, they get a little taste of the thrill that they got when they solved it the first time. And I feel like that as an experimentalist. I wonder, though, there are some puzzles and mysteries that are known to be unsolvable. I'll say something like Gödel's incompleteness theorem. It's known that mathematics, a formal mathematical system, is self-inconsistent in a sense, which is, we know that to be true. We don't know why that's true necessarily. I often find that about experimental physics as well, that experimental physicists such as myself have this desire to know what is scientific, what is worth pursuing. And some people don't want to pursue things like string theory. I want to ask you, what do you decide is worthy of your limited, we all have limited attention and time. How do you know when a mystery or a puzzle is worth solving, or may have it be known that it's unsolvable? How do you divide your time amongst these many activities?
Well, I think that that's part of having experience with various problems that we encounter. You get a sense of what is doable and what is not. And that's the difference between somebody who starts doing science at the beginning, like when I was a student, and now where I have seen many, many problems solved and some of them not being solved and so on. By seeing this through different kinds of projects and so on, you get a sense of what is doable and what is practical. So on the one hand, you know what is practical, what is doable. On the other hand, you have a sense of what is important and interesting. So then you take an overlap between these ideas, see, okay, among the ones which are potentially solvable, which ones are potentially more interesting and impactful, and then you kind of, based on that overlap, you decide what projects to work on. So that's usually how I go about doing it. So there could be many interesting questions that I would love to do it, but I have no idea, so therefore I wouldn't try those. But on the other hand, there are many things I could do immediately, but they sound like not that exciting or impactful. I won't waste my time with. So there's kind of like the intermediate line where you kind of try to do the most interesting thing you can do. And that combination of being able to and interesting is what needs to be both for me to feel like it's a good project.
So I was thinking as I read your book and thinking back to a conversation I had with Lenny Susskind last week about one of the most impressive characters in his mind in history, Aristarchus. And you mentioned Aristarchus as well in the book towards the end. And you talk about the fact that Aristarchus had these ideas about heliocentrism, which we now know to be true, but could not be proven because it was impossible to measure, for example, the parallax of stars at that time. In fact, it wasn't proven. The parallax was not proven until, I believe, the 1700s, even after Galileo. And yet Galileo had tools to actually prove Copernicus was right, and he didn't use them. Instead, he used other methods which turned out to be wrong. For example, his book, The Dialogue, was originally going to be titled On the Flux of the Tides. And he contended that the tides on Earth's oceans were caused by the motion of sloshing and revolution and rotation of the Earth, not, as we now know, from the gravitational influence of the moon. So he was overwhelmed by the kind of notion that Copernicus was right, so much so that he used incorrect evidence to justify and bolster the hypothesis. On the other hand, Aristarchus had the right idea, and Lenny calls him, the most interesting scientist perhaps in history, because he had the right idea, but the technology wasn't sufficient. What do you say to people who say string theory or studying the properties of black hole singularities, which we'll get to in a minute as well? What do you say to those people that say it's not worth spending any time on it because you can't falsify the singularity? You can't falsify string theory. It's so flexible, it predicts or accommodates way too many outcomes. How do you justify that? Is there an opportunity to appeal to future technology, as in the case of Galileo and Aristarchus? Eventually technology caught up and proved them right. Do you think the same thing will happen with string theory? And if not, why should we study it?
As you say, Brian, many of the things about string theory are at the level of predictions, theoretical predictions, that are very difficult to experimentally check with our current level of technology. So it's in some sense a promise for the future. So the question would be, as you say, why should we spend time on something that we cannot check in our lifetime as correct or incorrect and so forth? If there were no method to check our ideas, then I would have abandoned doing string theory for exactly that reason. However, due to the interesting interconnection of different ideas in high energy theoretical physics, you can actually check ideas theoretically. So you can check the validity of an idea from a different perspective and come to a conclusion whether that idea is correct or false without experimentation somewhat. Of course, that will validate the idea itself as being self-consistent, logically correct, mathematically consistent. Whether or not that's part of the explanation of our current universe, we still have to wait. But we have seen so much encouraging results from string theory in terms of its logical consistency in relation to different pieces of physics that we have discovered, like strong interaction, what kind of forces are working there, things about what happens for cosmology, what happens for black holes. We now know there are black holes very clearly. I mean, there's no doubt about them. And the fact that these ideas in string theory come to give a self-consistent picture to many aspects of them makes us believe in them. And like, for example, the prediction that Hawking made about black holes, the fact that black holes have entropy, despite the fact that Einstein's equations predicts that they are unique, his taking into account of the quantum mechanics, the work of Bekenstein and Hawking in particular, showed that no, there must be some degrees of freedom which are inside the black hole. There are some microstates. And the fact that string theory was able to account for those degrees of freedom, at least in specific classes of black holes, is already surprising and gives us a confidence that the theory hangs together. The details about how it would relate to our universe, can we understand the electron has such and such a mass, and so on, remains to be seen. But even now, I will give you one example. We can make predictions right now from string theory, which have experimentally been verified. Now, these predictions are rather, in a sense, you would say not as precise a prediction, but still is a prediction. And I will give you one example. So, for example, you take the electron, and it has a mass. And if you compute the mass of the electron in the fundamental units of physics, which is Planck mass, it's a very tiny mass. In Planck units, it's something of the order of 10 to the minus, 22 or 23. It's a very tiny number. So you say, great. Do we have any prediction that the electron mass should have been this small? Without knowing that there is an electron, and just by knowing that there is electric charge, and by knowing that there is dark energy in the universe, you find the bound for the electron mass. You find that the electron mass should be bounded by 10 to the minus 1 on the upper edge, and it's above 10 to the minus 31 on the lower edge. So the lower bound comes from the consideration of dark energy, and the upper bound comes from consideration of what is called the weak gravity conjecture, that gravity is always the weakest force in any consistent universe. So putting these together, you find a range for the mass of the electron, and lo and behold, 10 to the minus 23, which is the mass of the electron, is bigger than 10 to the minus 31 and smaller than 10 to the minus. So there are some predictions that you can see. Not as precise as we would typically like in physics.
That's right. I'm not going to write a grant proposal.
Right, exactly. But still, the idea that this has no falsifiable prediction is not correct. There are predictions that if the electron mass was somewhere outside this regime, you could have said, okay, this is inconsistent with these ideas. So therefore, there are some things arising from this.
I might gently push back and say, there are considerations in your book that you bring up from what's called naturalness that you could actually get the black hole entropy to within a factor of pi or so, just based on dimensional analysis. So that doesn't require any string theoretics at all. And you might also be able to push back. I might gently again, with respect, that that Weinberg made predictions about the value of dark energy, independent of the string landscape, but then it was eventually realized to accommodate that you'd have to have something like a landscape, which we'll get into in the multiverse. So is it unique to string theory, or if my smart undergraduate can derive it from her considerations of dimensional analysis, does it really count as a prediction of string theory, or could it equally be used by Fermi to say it's a type of Fermi calculation?
Okay, so good question. So let's go back to the black hole question you raised. First of all, even there it's not clear because consideration of dimensional analysis you mentioned presupposes that we make an assumption that the entropy of a black hole is related to the area of the black hole. And naively, we would have thought it's related to this volume. And that's not true. That was one of the surprising predictions of Hawking. So another dimensional analysis would have given you a totally wrong answer if we just use the volume. So you have to first assume it's area. Okay, let's assume it's area. Why should we get the factor of 1/4 of the area measured in Planck units? Why should it be 1/4? We don't know a priori from that calculation. Hawking's calculation shows it does. String prediction not only gives you that 1/4, but actually gives you an infinite further correction. It said this 1/4 of area plus a coefficient times log of the area, plus another coefficient divided by the area, plus another coefficient, infinite expansion in the area. So not only it gives you Hawking's answer, it gives you all the possible corrections to it. So it's not something that Hawking did not calculate. So from string theory, we not only get the leading term when the area is large, but subleading corrections when the area is not huge. So these subleading corrections shows you that there's a very clear picture of how you derive these statements, and not just the overall coefficient in front of the area term. So it hangs together. It is non-trivial, and to me, these are the kind of examples that bolsters our confidence in string theory and its validity. And other approaches people have tried does not give you something as concrete and as precise as we have seen in string theory.
So thank you. That's very masterfully explained. I actually came away just now with a new appreciation of the depth of the mysteriousness of that particular puzzle. So you're unifying mysteries and puzzles for me, Cumrun. You're to be congratulated.
My thumb's rather occupied right now holding up good old Carl Sagan, but yours is free to push that like button. And don't forget to subscribe. It really helps us with the algorithm. Now back to the episode.
So we talk about unification and symmetry later because I want to talk about hacking puzzle solving later on. Do you do crossword puzzles?
No, I don't.
Okay. You know who does a lot of crossword puzzles? Marilyn Simons, who's the wife of your good friend Jim Simons, who I believe you've written papers with not too long ago. We'll get to that in a little bit. But I want to talk about a conversation I had with Lenny last week, Lenny Susskind, your friend. And Lenny and I were talking about singularities. And I said to him, imagine if you get a note from God, although he doesn't believe in God, so you'll have to take my word for it. I said to him, imagine you get a note, and it says that actually there are no singularities at the center of black holes within the horizon. It's just purely classical. And furthermore, God gives you a note, and it says the universe follows the kind of cyclical eon hypothesis of Sir Roger Penrose, who's been on the show many times. And or a bouncing cosmology of my friend Paul Steinhardt and yours at Princeton, who's been on the show also many times. I'll put links to that. And so there's no singularity needed whatsoever. Why do we think that quantum mechanics needs to be married to gravity? In those two cases, to my mind, those are the only cases where I often hear my fellow friends and physicists, theorists mostly, they say, well, we have to unite gravity with quantum mechanics because of singularities. Well, what if there are no singularities? Would you still say that we need to have a theory of everything in that way?
No, I wouldn't. My problem with unifying quantum theory and gravity is far beyond, even if there were no singularities. I would have thought that it would be saying, like, could I have electrons which are quantum but protons which are not? To me, it's like that. It's not because there are different forces. The gravity is one of the forces. You could say, well, how about gauge forces be classical quantum, but the other one be quantum? There's no formalism in which that makes sense. You cannot talk about what is your formalism. Are you talking about how do you describe the physics in that context? It doesn't make sense. Now, you can treat classical gravity if you assume the gravity is not dynamical. In other words, if there's no graviton, if there's no mode classically that propagates. But that's not the case. We do know that there are gravitational waves, for example. So gravity is dynamical.
Well, we don't know that there are gravitons, but...
Well, there's a classical wave, I mean. So there's the fact that the wave comes, there's no doubt. So there's something moving. So that's what I mean by dynamical. In quantum mechanics, we call them made of gravitons, but regardless, there's something moving. And so the question is, how do you describe this moving wave in terms of classical physics or quantum physics? And so you cannot say, okay, if an electron, which is quantum, interacts with this classical wave, what does that mean? So that is a conundrum. I don't think singularities is the reason I believe gravity has to be described quantum mechanically. However, since you mentioned the singularities of the black hole, if the gravity were just classical, then you might think, oh, okay, this is bad, and the singularities are not possible, and therefore this incomplete, the theory. And therefore, one way out would be, yes, quantum mechanics resolves this singularity. Another resolution might be, as you say, for example, there could be higher order terms in Einstein's theory, which we have ignored, and if you put it back in, maybe gets rid of singularity or something. So to me, the nature of the singularity is not a convincing explanation of the existence of quantum description of gravity.
Thinking about the other property that people associate with black holes, actually, Lenny suggested that to him, the singularity is almost less interesting than what he calls the stretched horizon in some fashion in his books. The Black Hole War, his battle with Stephen Hawking to make the world safe for quantum mechanics. He claims the horizon is much more interesting from a quantum mechanical perspective. What do you make about that? Is the horizon of interest to those of us who are trying to unify gravity with quantum mechanics?
In a sense, I sympathize with that view that somehow universal aspects of black holes seem to be correlated with the properties of the horizon. So somehow a deep understanding of why and how that works seems to be a big piece of the puzzles of black holes. We know that the nature of the singularities and the structure of them changes by little assumptions that you might make. And so that's in some sense unstable kind of a question. But the horizon is robust. Somehow the existence of the horizons and the properties of the horizons and what do we think about measurability or immeasurability of horizon, those are more robust questions. So I agree with that viewpoint.
And I had Juan Maldacena, who's another friend of yours, on the show, and we talked a lot about about wormholes, and in fact, humanly traversable wormholes. I want to get your opinion on why do you think someone as bright as Juan, who you reference in the book, why would he spend his time on something which is, surely inaccessible for quite some time? Do you think this is a fruitful use of his time?
I think probably you asked him, or you could ask him, but I think that the ideas of wormhole is just understanding wormhole is to try to understand what we think about quantum gravity can do. I don't think he's necessarily thinking about science fiction kind of wormholes, even though he might even talk about those, the traversable ones. But the idea of studying wormholes, I think, was studied many decades ago, but even more recently in works that arose, for example, Lenny and Juan worked on connection between Einstein-Podolsky-Rosen paradox and Einstein-Rosen bridge, which is this wormhole geometry. Mm-hmm. So the connecting them and so forth shows that certain things that might be whose understanding enriches connecting different parts of physics, perhaps motivates one to study wormholes more vigorously. Traversability, whether we can send a spaceship there, this and that, and so on, is at this point not in the cards for our universe. We don't see that. Our understanding does not necessarily lend to that direction. But I think I would not be deterred, nor would I find this more overwhelming reason to study wormholes. I think we should study them regardless.
Yeah, his response to me on the podcast was that he has found it a fruitful way to understand quantum mechanics and gravitational fields. So he views it as fruitful and important. And yet there are criticisms of the work on which that paper is based upon, a series of papers he's written on wormholes and traversable wormholes, in that they rely on results that are completely unproven and perhaps unacceptable by your colleague and my friend Lisa Randall and her colleague Sundram, which are these 5-dimensional universes, or they rely on Juan's major contribution, these ADS CFT kind of dualities. Those are things we don't believe we live in 5 dimensions, and we don't believe that we live in ADS. If anything, it seems more likely after I read your book that we live in a DS, not ADS. So again, these questions of are they just merely, I could also point to a crossword puzzle or a Rubik's Cube and say they're very challenging. You're very smart if you can solve them. My kids can solve them. I can't solve them. I take apart the Rubik's Cube. It turns out you can put it back together, take it apart, and no one will know that you did it. Although I joked once, Cumrun, I wonder if you'll get this joke. I said I got to the point where I could solve 5 sides of the Rubik's Cube, but I just can't get the 6th side.
Right, that's a good one.
So, but anyway, getting back to this, 5-dimensional random syndrome, background space-times. ADS, where we don't live in an ADS universe. Again, it just seems like adding on higher order speculation when, it's hard to justify that. And I'm not saying that only as an experimentalist. There are theoreticians that will say the same thing. Why don't they spend their time working on, calculating some cross sections or whatever? I don't know what theorists do, to be honest with you. But is it not, kind of speculative to study these things unless you feel like you're learning about math, and that's important to learn about 5-dimensional space-time and ADS CFT. Where do you stand on that?
Let me say instead of that specific one, because I think let me just change your question a little bit. The questions are, why do we spend our time on theoretical questions which are not directly relevant to our universe? I think you're giving that through examples of, for example, 5 dimensions or anti-de Sitter space or this and that. So I will try to give you a motivation for how we come about that. So what do we know about our universe? Well, we know it's made of particles, electrons, quarks, photons, this and that, and there are forces between them. Great. What do we know about their forces? Well, we know quite a bit. We know what is called the Standard Model describes the forces between them. The Standard Model consists of various kind of forces, the electroweak forces, the strong forces, and so on. And within this context, we understand how these particles interact with forces. Okay, now you come to asking why. Why do we have this particle? Why do we have this force? Can we have other kinds of forces? So this is the beginning of a question. Could we have, for example, in our universe, instead of having this finite number of gauge groups, billions of gluons or billions of photons or Why do you have just one little photon? Why do you have only one strong force? Why don't we have much more? In fact, if you were to write a random theory in 4 dimensions, which is consistent with quantum field theory, with Feynman's rules of calculations and everything, you would naively say, okay, it could be like a gauge group with, billions of gluons and this many particles and that many. But no, we only see very few particles with very few forces around. Why? Okay. Now you might say, well, this is metaphysics. I have no idea why. I don't care about it. On the other hand, a lot of people would like to have a deeper understanding of not only what are the forces and the dictionary or geography or geology of what are the particle names or whatnot, but why? Why do we have so many few of them? Why don't we have more exotic situations and so on? So that's a question. Now I will give you a parallel question within string theory for which we now have an answer. You start with asking, okay, the situation we live in, this with all the particles and all that, is very complicated. It's very messy. Can I idealize it? And the answer is yes, you can idealize it. Idealize, you still can be in 4 dimensions. You can be almost in flat space like the universe we live in, like Minkowski space. But let's add some ingredient which is not in our universe, and that ingredient is supersymmetry. Suppose I say I have a maximal amount of supersymmetry to simplify my task, subject to only the assumption that I have some gauge forces around. So what is the maximal amount of supersymmetry I can have, which gives me gauge forces like gluons and so on? That's what's called n equals to 4 supersymmetric theories in 4 dimensions. Fine. So you restrict your attention to that. Then you ask, within this class, do I have any reason that the number of gluons are finite? Now, if you don't include gravity in the discussion, it turns out you have no bounds. You can perfectly understand these theories, and you can have arbitrarily large number of gluons in that theory. However, if you include the gravity, it turns out that the group choices are finite. You cannot have arbitrarily big group. So it turns out the rank of the group should be less than or equal to 22. So out of an infinite number of possibilities, somehow just including gravity, questions involving consistency of gravity mixing with the rest fixes what are the particle spectrum in that theory and what are the possible forces and so on. So that means the question of gravity in that context shows us crucial to answering these questions. So now you say, well, we don't live in supersymmetric theory, so why do I care about this? This proves the concept that gravity can restrict what are the possible content of the forces that we see around us. Of course, we hope to extend these kind of arguments to the universes like ours, which have less supersymmetry or no supersymmetry. But that proof of concept is what motivates us that yes, perhaps the answer is good. Toy model is a cherished approach in physics. We always start with saying, let's study the harmonic oscillator of this or that. That's a toy model. The harmonic oscillator really doesn't exist. The idealized one is only idealized thought. But we always do it. That's physics. The physics is precisely modeling. So string theory is at the worst case, a model of what our universe could look like. Mm-hmm. And so at the very, very rudimentary form is that we want to say, okay, a structure which is like string theory, how could it potentially give a universe like our universe? Mm-hmm. And so that kind of juxtaposition is very similar to the well-honored tradition of harmonic oscillator as toy models of certain physics concepts we want to understand.
Is there any observation or lack of observation that would cause you to abandon string theory?
I think that abandoning is a strong word for it for me. I think for me, there's no substitute. If you give me a theoretical substitute for string theory, which is better in some way and has explained at least as much as string theory has done, then I will abandon it. But nothing like this is in the cards. I think if we understand that there are some obvious predictions of string theory which are ruled out in some form, then we go back. I will go back and search my understanding of string theory, and perhaps we made a mistake somehow with our understanding, because I think part of an issue is that we don't have a complete formulation of what string theory is, so we are kind of on a difficult platform to be that sure is string theory right, is string theory false. To do that, you have to know exactly what string theory is, and we don't know that yet. Mm-hmm. So I would go back and check my understanding of the subject.
And correspondingly, what about supersymmetry? Where would you say we are in terms of your credulity or Bayesian prior on that veracity of supersymmetry?
Well, I see that my prior right now is the supersymmetry is not there in anywhere near our energy scales in Large Hadron Collider. But I would say that there is my high prior with the sufficiently high energy could be all the way to Planck energies. You might restore some supersymmetry. So I think that supersymmetry is in some sense a good prior, but I wouldn't say that that's a necessary ingredient for string theory. Mm-hmm. We do have models in string theory where no supersymmetry arises. Some people, some of my colleagues, I don't know why, they kind of say supersymmetry is a prediction of string theory. I wouldn't go that far. There are models within string theory which are perfectly fine and have no supersymmetry.
I want to read the passage from the book towards the end about gauge symmetry. You say many important properties of particle physics involve what are called gauge symmetries. These involve somewhat different flavor than more familiar symmetries we see all around us. With regard to translational symmetry, you might say an experiment performed in the two different points should have the same result. With regard to gauge symmetry, we might say that these two different points are essentially the same point. What does that mean? And how do physicists use gauge theory or symmetry as sort of a hack to solve puzzles?
So first of all, what is gauge symmetry? Gauge symmetry is a symmetry that you kind of want to delete in a sense. It's a very strange symmetry. So let me explain what that means. An example of it is discussed in that same chapter that you mentioned in the book. Suppose you talk about the exchange rate, let's say between the US dollar and euro. You have some exchange, like, whatever, one euro, let's say is $1.2. Okay, fine. Suppose the European Union decides tomorrow to change the units of their money, and the what used to be 1 euro now becomes 100 euros. Okay, then the exchange rate between the US dollar and the euro will change by a factor of 100. That's what we call gauge symmetry. We will say in this context, there's a symmetry which tells you that rate has to get multiplied by a factor of 100 or divided by a factor of 100 appropriately. Is it a deep fact? Well, it's just the renaming of what you mean by your unit. That's all. So gauge symmetry is like that. So it's a redundancy of a definition. It's not a fundamental number there. It's just if you change your units, that number changes. That's all. And so gauge symmetry is akin to that statement. Now, why that should come up with so much power in terms of applicability in our universe is not obvious. Why should our universe be made of gauge forces and so forth? Why should we be dealing with forces in that form? And that requires a further thought. And that turns out to be the basic statement is the following, is that if you look at a property called unitarity, which is needed for consistency of a quantum theory, which basically means the probability of something happening is 1, it turns out that the spin of light particles is less than or equal to 2. And so if you look at the bosons with spin less than or equal to 2, there are only 3 choices, 2, 1, and 0. And spin 2 is graviton, and spin 0 is like Higgs particle, and spin 1 is like a gauge particle. So the existence of gauge symmetry is needed to make spin 1 theory work. So you cannot describe a spin 1 particle without this redundancy. So just from this picture, we are forced to have this redundancy. So I would say that the notion is to trying to make sense of a particle which has a spin 1 forces us to consider gauge symmetry.
And I was thinking about that in the context. I also talked about that particular problem with Juan Maldacena. And he referred me also, of course, to some of the original work was by Pia Milani and Eric Weinstein on a particular example of deriving Maxwell's equations from it. I was wondering, it's not so often I'll get a chance to run a crazy idea by someone as eminent as you, Cumrun, but could we not also use an example from language? In other words, as Shakespeare said, a rose by any other name would smell as sweet. Is that another example of a gauge transformation? And
yes.
So is there anything we could do with it?
I don't know if you're saying gauge. I think that the main thing is not that mention of that symmetry, but that idea is needed for spin 1 to make sense, spin 1 particles to make sense. Spin 1 massless particles to make sense need that. Now, why it needed, we can understand, we can explain it in the context of particle physics, but by itself, a redundancy and a name should not be that important. And in some sense, gauge symmetry is encoding redundancy.
Yeah, I had a conversation with Noam Chomsky about that as well, kind of what we call something. And in the words of Richard Feynman, who would say, just because you know the name of something doesn't mean you know that thing. And I want to get to Feynman in just a little bit. One of the other delightful things about this book, and we're talking with Professor Cumrun Vafa, Harvard University about his wonderful new book, Puzzles to Unravel the Universe, which is just quite spectacular. Is this notion that that there are sort of hacks and tricks that we can use to unravel certain puzzles, but that some puzzles, by their nature, have this mysterious quality to them. And one thing that you spend a lot of time on, which I'm very fascinated by, is God and religion. And I'm a practicing Jew myself, and I always say I don't know if I believe in God, but I believe in religion. I think there are things that religion can do, and it's practiced properly, that can benefit a person's life. The absence of working one day a week is a very big thing in my life, and it contributes to my sanity. The Sabbath every day, every week. I don't work. I don't send emails. I don't tweet. I don't text. That's kind of a commitment to a religion, if not a God. I want to ask you a few questions about that. Some of the greatest minds in history were religious believers. Isaac Newton, you mentioned in the book, you don't mention this aspect of him, but his biggest accomplishment, according to him, this is a man who came up with the Principia, invented calculus, the universal law of universal gravitation. He said his biggest accomplishment was being Christ-like. In other words, that he never married, he never had relationships with women in that way, and that way he dedicated his life to pursuit of knowledge. Of course, he also practiced alchemy and did other things. But what can you say about the role of religion in your life, in this book? What does it mean to you? And obviously you don't proselytize at all, but you seek a harmonization, a consilience between religion and God. It reminds me of your former late great colleague there, Stephen Jay Gould. What can you say about the role of religion in your life, and maybe even as a physicist, if that's applicable?
Well, I did not talk about the role of religion in my life. I try to keep it out of the public view. I keep that completely private. So I would not discuss that aspect, but I will instead say that religion and science are neither contradictory nor reinforcing each other. In my view, they are two separate domains of thoughts or beliefs. And I just in that chapter in that book, I try to explain why I felt that trying to prove or disprove the existence of God, the religion, and so on is a futile task in the context of science. And I try to also say the opposite, that if scientists feel that they can disprove or say that religion is useless, I also discounted that too by giving counterexamples, including the Lamatre understanding of proposal that the universe may have come from the beginning of some primordial existence, which something Einstein refused to accept and called, I don't know if it's how true the statement is, but Christian mythology. I'm not sure if that is what actually happened, but the main point is that being motivated by religion is not necessarily a bad idea, as the examples show. Newton is another example. On the other hand, some people do great without religion. People like Hawking and so on were perfectly fine with exploring their ideas completely free of any such assumptions, and they did great work too. So I don't try to make a statement really about what it should or shouldn't be. And my views, I kept it to myself because I didn't feel I have anything to offer in terms of advice or anything to anybody. So I just said there's no point me sharing what I feel it should be or shouldn't be. But I think listening to other scientists who have felt strongly about it one way or the other, and seeing, okay, what does it tell us about the role of science for their life and for religion and science, how they mix in their lives, was useful perhaps. But then I also thought that it would fit with my book because, it's a serious discussion, science and religion. And the book I'm talking about, puzzles, sounds like a very, fun kind of thing. It's a little less serious. So trying to bring those two subjects, a very serious subject with a very casual topic, puzzles, I thought it'd be an interesting combination. I was trying to bring puzzles to lighten up the mood, so to speak, that, okay, there are these serious discussions, but let's talk about puzzles in this context. And I offered a few puzzles. Some of my favorite puzzles are actually in that chapter. So I think I just use it as a springboard for discussions, really. I didn't want to offer anything specific. But I think the main thing I wanted to convey in that thing is we should be tolerant of viewpoints. And that was basically I was driving in that chapter.
Yeah, we hear a lot about the hostility of science to religion. I always point out that the word Torah, which is a Hebrew word for the Bible, the Old Testament, it doesn't mean knowledge, which is what the word science means in Greek. Science, or Latin rather, means knowledge. And Torah means wisdom and teaching. So there really are, as your late great colleague Stephen Jay Gould would say, non-overlapping magisteria. They don't necessarily have to interfere with each other. Now, I always also point out that in the book of Genesis, at least, again, I'm not proselytizing. Again, I consider myself a devout agnostic, which is something I think I have in common with the late great Freeman J. Dyson, who's a friend of mine and a friend of my shows. Many times did he appear on it. He used to say, well, the existence or lack thereof of God is a great mystery, and scientists love mysteries, and we love puzzles. And maybe you can solve it. Maybe it's a mystery, or maybe it's a puzzle. We don't know. But to give permission, as you do, to at least consider it and have an eminent scientist such as yourself. It's one thing if I try to defend religion, but someone of your stature defending,
right?
Yeah. Well, I'm just saying it's delightful to have that you're not scared of it, and that you are quite comfortable. But again, you're not proselytized. This book is not a book about why you should believe in a particular religion whatsoever. So I just want to commend you on that. I found it so refreshing and delightful. I want to talk just in the last few minutes. I know you're super busy today, but there are many mysteries that I think are in the theoretical physics world. There's a particular researcher who's a friend of mine, a friend of the show. Her name is Sabine Hassenfelder. She's in Germany as a research scientist. And she made a video last week kind of criticizing Lenny, Susskind, and others, and even Hawking, with the black hole information paradox, claiming that, in her words, and she's had nothing much good to say about physics, theoretical physics' progress in the last 40 years, according to her, it's been stagnant. But anyway, she criticizes the black hole information paradox as the biggest overhyped bit of physics that's ever come along. I think that's a little bit over the top, but her point is that these the laws and so forth that govern this are completely kind of more or less pedestrian, and furthermore, they can't be solved because we don't know if Hawking radiation exists, and we can never measure it. So a lot of these things, even from a pragmatist point of view, are somewhat pointless. Maybe this is relevant to what we talked about earlier. If so, we don't really have to dwell on it. But why do you think that there is so much attention to things like black hole information, or the multiverse, which we'll maybe close out the scientific portion of the podcast with? Why is there so much interest in that? And the double slit experiment, EPR, and all these things. Why does the public get so wrapped up in this? And do physicists maybe do a disservice by overhyping things like this?
Before I get to this, I think people who talk about subjects like black hole and so on, and especially criticizing or whatever from outside, they could do that perhaps if they had a scientific standing. And by that, I mean not just to say, well, I have read physics, I've got my PhD in physics, therefore I can say whatever I want. I think if you have not done sufficient research yourself in some direction to try to criticize somebody else, I think is a little bit suspect. So that's some of the comments. So it's like throwing a stone at a building or glass things because you're not inside. And so that to me is a bit of a childish reaction. As far as more seriously, okay, so why is it that we think is an exciting subject and so on? Well, it's exciting because it was a mystery. It's still to some extent a little mystery. And mysteries always guide new physics. And so for us, that's the reason we study black hole. Of course, black hole sounds, captures one's imagination. What if you fall in it? What if a black hole is near us and this and that? So it can easily captivate public. But that's not necessarily the reason we are talking about it. The reason we are talking about it is that many of the mysteries of fundamental physics seems to be wrapped up in it. And that aspect to us is what is fascinating. And yes, of course, it will be interesting when you want to describe what we are doing to general public to explain that link, because the general public can hold on to that concept as being interesting because they can feel it. Oh, black hole, that's fun, that's cool, that's strange, that's exotic. Let's see what we have to say about it. So to say that we are excited about it is not because we want to kind of get the public going with excitement. We are excited about it because I think many of our deep questions are related to enigma of black holes. and a lot of them can be reformulated as properties of black hole. You lose information. If you throw something into the black hole, can you figure out later on what was it that you threw in? Or after the black hole evaporates, there's zero information? That's the information loss. In other words, understanding that process tells you the meaning of fundamental meaning of whether or not the theory can or cannot lose information. Black hole is a way to ask that question, and that turned out to be deeply related to many other aspects of the theory. So for us, it is that aspect. Now, to undermine it, to say, no, it doesn't radiate, or it doesn't radiate, we cannot measure it, therefore it's a bad question, all that is, again, the kind of things that it sounds like this parallax that you mentioned, this experiment that later on we were able to do, but right now we cannot do, was that, oh yeah, are the stars really, far away or infinitely far away? What is it? What is the connection with why don't they seem to move? And they indeed move, it just have not enough accuracy. Same with black hole. If you try to say at that time, thinking about them at finite distance and has a meaning would have sounded crazy during the Greek time, perhaps to some people, but we now know that's not the right way of asking. Of course, the people who said that that's a bad question to ask because you cannot resolve it would have won in the short term, because yes, in the short term, you cannot measure it. The parallax was not possible to measure. But was it a bad thing to raise? No, it wasn't a bad thing to raise. And so we have learned that through history, what we should pay attention to. And I think that people who throw stones rather than alternatives are never the ones who create the new science. And so there's one thing to have a constructive criticism of a theory, to say, oh, you know what? Your theory typically wants to have, let's say, 5 dimensions. Why not 4? Okay, let's try to find the model why 4-dimensional space-time arises, and so on. That's a good question. We are not saying we have understood that. But to say, oh no, this is bad, and so forth, without any given alternative, I think it's just disservice to science. And to be frankly, it's just, I think, to try to get publicity for the sake of publicity, to try to say something. And to me, controversial statement just to attract attention, I think, is unfortunate.
I mean, to be fair to her, she does say that she's written papers about this subject herself. But yeah, it certainly takes out a lot of aggression. But no, I think it's important to hear the voices, as long as you say they're acting towards a maybe not necessarily conciliatory perspective, but a congenial perspective. They're trying to do something constructive. I agree with that. I want to conclude the scientific portion just asking along the lines of, I talked with Shelley Glashow last week, and he has a wonderful book called Interactions, written in 1988. And in that book, towards the end, he has a series of questions for the future that he suspected would be answered in the superconducting super collider and other things. Of course, that wasn't to be. But the question of something like the Higgs, he just assumed that we would understand the mass of the Higgs in not too distant future. Yes, we didn't learn it from the superconducting super collider, but we found it out eventually. But he goes through other questions, which in my mind are much deeper. And it was quite a treat and a delight for me to go over this scorecard with him and have this eminent, Harvard professor, Boston University, give a score, F, because some of the things that he listed on there, aside from, our neutrinos massless, which we now know, which we didn't know back then, that they're not massless. At least one of them is not massless. Maybe 2 are not massless, rather. But nevertheless, why are there 3, generations of quarks? Why are there so many fundamental parameters? Why are there so many particles? What is the fundamental dimensions of space-time? Those things we haven't really learned much about. And I'm not going to ask you to comment on those. There was 1 or 2, as I said, the Higgs wasn't even mentioned, but the neutrino mass being non-zero was. The proton's lifetime, he thought, at that time it was like 10 to the 28th years. Now we think it's much bigger, maybe 1,000 times longer. And that had some implications for supersymmetry. I want to ask you your scorecard. What would you give our understanding of things like the multiverse, the string landscape? What kind of grades would you give to such subjects currently? And then what kinds of things would you want when the next edition of Puzzles comes out, hopefully in 30 years after becoming an international bestseller?
Thank you. I think that the scorecard, the score you give to something is based on whether or not good attempts have been made and how much progress has been made compared to the difficulties ahead. So when you measure it against how much complication is on the way, I would give it A+. if you ask me if the scorecard is to try to measure how close we are to finally settling it, I'll get it F or very close to F. So it depends on what is the scorecard for. So we are very far, unfortunately, still from making a prediction which is really precise and quantitative, and we can say this is a definite prediction of string theory. It's either this or the whole thing falls apart, and it's very precise. We are not there yet, by far. So it depends on that. I would say that as far as the scorecard, I would view it as what is possible to do in terms of theoretical, and huge things have been learned. I think to underestimate the dualities, that meaning of the dualities that we have learned, it's remarkable how much we have learned. For example, you mentioned this question that Shelley raised. Will we know the fundamental dimension of space-time? We have learned something about this. We have learned that's a bad question. Why is it a bad question? We have learned that question depends on which viewpoint you have. There is no fundamental answer to that question. It depends on which parameter regimes you look at. So the dimension is not a fundamental concept. Even that realization that you cannot settle that question is a bad question. It's only in one corner you can say it's this, in a different corner is a different number, so it's not an invariant concept. Those are progress. So for us, we have made progresses in that form. So conceptual progress is what I would say is certainly has happened. Holography is another amazing conceptual progress. Dualism more generally is. And so I think we are learning quite a bit. I think the progress is going to be not super fast if we are measuring it against the yardstick of connecting to experiments, but if in terms of what new things we have learned, it's huge. We have learned a huge amount, and it continues to unravel.
Cumrun, thank you. If you have just a few more minutes, I would like to ask you some questions I ask all of my guests on the show. Is that okay?
Sure, please go ahead.
Great. So the first one in Judaism, in the Hebrew language, there's a concept of what's called an ethical will. And that differs from a material will in that it is not bequeathing monetary or material objects to your offspring, but instead is bequeathing wisdom and discoveries that you've made outside the material world. And it's meant to benefit not only your biological children, one of whom put me in touch with you. So I want to thank that particular Vafa son for putting me in touch through the magical medium of Twitter.
Yes, beyond my son, yes.
Yeah, so thank him very much. And when this comes out, we'll send it to him to share. But I want to ask you, not only for him and his brothers, but for the whole world, what would you put in an ethical will, a will of wisdom, not only for your biological children, but for your ideological children, of which I count myself as one?
Thank you. It's a great question. I would say the following, and I was preface it by saying where this wisdom may come from. It's from the realization of the importance of duality in physics. What we have learned, and I think this is a broader application, is that the best viewpoint about the subject depends on the question being asked. There is no best viewpoint, and that best viewpoint is subject to the question. So that also opens up our mind to be open-minded, that we should not say this is the way to look at it, everything else is bad, and so on and so forth. We have learned that contradictory sounding views are sometimes necessary to understand the subject. Contradictory sounding views, which are nevertheless consistent, but in a subtle way, turn out to be the beautiful aspects that dualities have shown can happen. And so, in my opinion, openness and the fact that duality shows us that multitude of attitudes and views is important to appreciate and connect, not only in a scientific context, but in a broader human societal aspect, I think could have a good applications.
Very nice. So I don't know if you're a science fiction fan, but Shelley is a huge science fiction fan. And I asked him about Arthur C. Clarke, who is the namesake of the center that I act as a co-director. And he had written the book on which the movie 2001: A Space Odyssey is based. So have you seen that movie, or are you like Shelley?
You have seen.
You have seen it?
Yes.
Good. So you might remember in that movie, in the opening scene, there are these primates in Africa, and they discover this obelisk, this monolith, this black ominous structure.
Right.
That's placed there. And then later, they don't know what to do with it. They hit it with a bone or something. And then later, you see it's on the moon, and astronauts are encountering it. You know, they've obviously developed. I want to ask you, and it's sort of meant as a time capsule, meant to be discovered when humanity is ready for this knowledge. I wonder if you knew you could make a billion-year-long lasting time capsule, what would you put on it or in it? What would it encapsulate?
I think billion years down the line, what I would think now is probably going to be irrelevant. And so one of the things I believe in is our knowledge is continually evolving, and almost none of the things that we think are correct now is going to stand up to be exactly correct. There are going to be good approximations, there are going to be modifications and so on. So to try to put something so solid for future, I would feel hesitant for that reason, if nothing else. However, if we want to brag about something we have learned in our society, in science, you can put some aspects of, I don't know, this and that theory to show that, yeah, we have a string, for example, we have understood this much. Of course, 100,000, 10,000 years down the line, they might laugh at us. Okay, they understood something, not too much, but okay. Just like the way we look at what scientists were doing 3,000 years ago. We don't think they were really at the cutting edge of things. Now we kind of say, okay, that was fun. They were smart people, but maybe not for answering this and this and that. So I'll be hesitant to put my word of wisdom in any form for the future generation. I hope that they would not laugh too hard at us. That's all.
Although at least two ancient Greeks, actually three ancient Greeks, Plato, Archimedes, and Aristarchus, make very prominent appearances in your delightful book. Yeah, it's just what you said reminds me of what Richard Feynman said about, I didn't get to ask him this question, but he said, if in some cataclysm all scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling, barely being squeezed onto one another. In that sentence, you'll see an enormous amount of information about the world, if just a little imagination and thinking are applied. And of course, this is the Arthur C. Clarke Center for Human Imagination. So I've managed to unify Feynman, Plato, Aristarchus, Aristotle, and the great Cumrun Vafa, who will go down.
One sentence to that, maybe.
What's that?
I would add maybe one little footnote to that sentence.
Go for it.
Atoms and extended objects like strings.
Okay. Okay, that's bold. Yeah, as Yogi Berra said, the great prognosticator, he said, it's difficult to make predictions, especially about the future.
Yes, exactly.
Okay, the last sentence, the last question I ask all my guests, Cumrun, relates to Arthur C. Clarke as well. He had these famous 3 laws, one of which was any sufficiently advanced technology is indistinguishable from magic. He had another saying called his second law, which was that for every expert, there's an equal and opposite expert. And then his third law says, the only way of discovering the limits of the possible is to venture a little way past them into the impossible. And that's the origin of the name of my podcast. I want to ask you, what advice would you give to a young Cumrun Vafa? What things seemed impossible when you were a young person, but now, because you had courage and you went into the impossible, now seems doable to you, and if only in hindsight?
To me, math was always attractive. The ideas of math hanging together, the beauty of Euclidean geometry, understanding the relation of simple objects. And I also was always fascinated by, things around us, like, how does the whole thing work? Why there are atoms? How does this work and that work and this one? And these two things sounded to me like separate universes, like math, Euclidean geometry, and so on is there. And then you have this real world that's around us, and has nothing a priori to do with this math. To try to bring these two universes together or closer, first of all, I noticed not only that there are already big links between them through centuries of work when I got to learn more, but then I felt, could they become even closer and in fact indispensable for one another? And so when in the context of string theory, the two have come together in such a way that you cannot do one without the other. You cannot do physics without math. And now also, you cannot do math without physics. So the fact that these things can be combined is something that is really pleasurable for me in terms of my own interest. But I think anybody has their own interest, and I hope that everybody follows what they are deeply passionate about. And, there are things which are fashionable today or may not be fashionable tomorrow and so forth. But whatever you're excited by, if you follow it, regardless of being fashionable or not fashionable, gives you pleasure. And usually by that action, you're thinking deeply about it, you will convey something important to the rest. So I think follow your dreams is is a cliche, but I think is the correct cliche in this case.
Yes, and as you say in the beginning of the book, you dedicate it to your parents, as well as your family, Simeon and Javad, for nurturing your curiosity. And I think that's so delightful that you have now shared this curious the investigator perspective that you bring uniquely. You're a towering figure in science, and I really appreciate your time. I have to go now to paint the surface of Gabriel's horn. It's going to keep me busy, right?
Yes, it will. A very, very long time. Maybe 50 time, but it was a pleasure, Brian, to talk with you, and very enjoyable discussion and questions. Thank you for having me on your podcast.